There is no question that computers have changed the world, and today we have computers everywhere. We have them in our homes, but they're also built into our cars and even our watches, and we often take for granted easy access to such computational power. But it was really the predecessors to those ubiquitous computers that first changed the world and made things once thought to be impossible commonplace. And one of the places where those changes occur was at the NASA Ames Research Center in California, which is today home to NASA's Advanced Supercomputing Division. The work done there on some of the world's first supercomputers deserves to be remembered. NASA's Ames Research Center was founded in 1939 as the second laboratory for the National Advisory Committee for Aeronautics, or NACA. NACA was dissolved in 1958 when its assets and personnel were transferred to the newly founded NASA. The Research Center was named after a founding member and longtime chairman of the NACA, Joseph Sweetman Ames, after his death in 1943. Central to the history of the Ames Center are its wind tunnels. In the 1940s, wind tunnels were built at the site to test and refine all manner of aeronautic equipment, from planes to guided missiles to satellites and re-entry vehicles. Several of the most important were the 40 by 80 foot wind tunnel opened in 1944, which was intended to assist with aircraft development, the 12-foot subsonic wind tunnel opened in 1946, and the Unitary Planned Wind Tunnel opened in 1955, in which nearly all of NASA's crewed space vehicles were tested. Ames' research in wind tunnels and aeronautics was a core part of their later work with supercomputers. The concept of supercomputing is not new. The term was first used in the 1920s. A 1929 New York World article used the term to describe custom-built tabulators designed by IBM for Columbia University. Those tabulators were not much like modern supercomputers, but represented the concept that supercomputers were specially designed and extremely powerful computers. In the 1950s, some of the earliest supercomputers and designs were built. 1955 saw the release of the Harwell Cadet, possibly the world's first fully transistorized computer, a massive improvement over earlier computers which relied on vacuum tubes. The transistorized IBM 608 was also announced in 1955 and may have been demonstrated in 1954 before Cadet. Cadet had 64K of memory. The world of supercomputers really began with the formation of the Control Data Corporation in Minneapolis in 1957. CDC was joined by Seymour Cray a few months later, and in 1960, Cray completed work on the CDC 1604, fully transistorized, and the fastest computer in the world when it was released. Cray's work was founded in his belief that there would always be a need for a machine 100 times more powerful than anything available today. Cray almost immediately set his sights on building an even faster computer, one that was 50 times faster than the 1604. Along with numerous other CDC engineers like Jim Thornton, he developed the CDC 6600. The 6600 was 3 times faster than the IBM 7030 Stretch, which previously held the record and is often considered the world's first supercomputer. IBM CEO Thomas Watson Jr. complained that the system was developed by only 34 people, including the janitor, and that he failed to understand why we have lost our industry leadership position by letting someone else offer the world's most powerful computer. The 6600 was extremely powerful for its time, with performance up to 3 megaflops, or 3 million floating point operations per second. It was an era-defining computer. It became one of the most successful computers of the period. More than 100 were sold at as much as $9 million per computer. NASA received its first supercomputers in the 1970s when the ILIAC 4 parallel computer was installed at Ames Research Center, and the CDC Star 100 vector computer was installed at NASA's Langley Research Center. These computers were early examples, and while only marginally successful, they provided a valuable testbed for the new kinds of computing. The connection between the supercomputers designed by people like Cray and the work at Ames began in the 1970s, when engineers there began wondering if the complex and expensive work done in the wind tunnels could be done using simulations, by using extremely complicated math called computational fluid dynamics, or CFD. CFD equations are so complex that they required an extremely powerful computer with even more capability than the CDC 6600. Ames Center Director Hans Mark was impressed with improvements to nuclear reactors enabled by computer modeling and believed a numerical wind tunnel could be used in aeronautics. In 1978, several Ames researchers, F. Ron Bailey, K.G. Stevens Jr., Wayne Hathaway, and Ray Lim, began working on formulating the computational requirements to solve three-dimensional fluid dynamics equations. Bailey said that of particular interest was transonic flow, in which airflow around an aircraft travels at both subsonic and supersonic speeds, a flight condition that was challenging to analyze via wind tunnels. Military plane tactics were changing to focus on maneuverability at transonic speeds, as air combat during the war in Vietnam was shown to be fought at relatively slow speeds. Other issues were appearing, such as transonic drag rise. At around 85% of the speed of sound, aircraft develop a supersonic flow in some areas that increases drag. Wind tunnels successfully tested a number of things, but were bad at obtaining transonic data because of ventilation, as well as interference caused by the tunnel's walls and the support that held the physical models in place. Numerous aircraft developed at NASA had already seen issues from the wind tunnel's limitations. In 1983, a NASA technical memorandum described many of the requirements for robust computing capability under the Numerical Aerodynamic Simulation, or NAS program. Computational aerodynamics, the engineers wrote, is being restrained by the lack of suitably powerful computational systems. Solving such fluid dynamic equations without approximation requires unrealistically large amounts of computation for all but the most elementary flow situations. NAS's goal was to provide leading-edge computational capability to the aerospace community. Experimentation by the way of wind tunnels was not obsolete, but computer simulations, if they could successfully be done, could account for numerous things that wind tunnels failed to simulate. In their technical memorandum outlining the need for numerical aerodynamic simulation, the researchers pointed directly to numerous aircraft which had problems that were only discovered after prototypes were tested in flight. For example, several military aircraft ran into expensive design changes after prototypes were built, while flight tests of at least 2 civilian transports found that the wind tunnel experiments had incorrectly predicted nacelle wing interference, requiring a redesign of the aircraft. The researchers estimated that to approximate the most complex equations needed for the design of next-generation aircraft, 3 million to 3 billion computers with contemporary processing power would be necessary. Computing technology was simultaneously improving rapidly, especially under the care of Seymour Cray. After delivering the 6600, Cray went on to work on the CDC 7600, which had computational speeds 10 times faster than its predecessor. Cray hoped to continue to increase the speeds of his computers, but CDC was unwilling to put more money on the line for his planned follow-up, the 8600, as both of his previous designs had threatened to bankrupt the company before their release. Cray left CDC in 1972 and, with ample funding from Wall Street, released the Cray 1 in 1976. The Cray 1 was an impressive machine with a 64-bit processor and 8.39 megabytes of memory. It beat nearly all similar computers in terms of speed. The only computer close in comparison was the Iliac 4, itself never meant to be a commercial machine. The Cray 1 was a major success, and over 100 of the machines were sold for as much as $8.8 million. At Ames, research using supercomputers for simulation purposes continued, and in 1982, Peter Bunning created the Plot 3D software program that provided a file format still in use today for storing structured grid and results data for computational fluid dynamics simulations. The following year, NAS purchased its first hardware, 2 Super Minicomputer Digital Equipment Corporation VAX 11/750s that they named Wilbur and Orville. It was that year that researchers first used computational fluid dynamics to generate solutions for the Space Shuttle main engine, hot gas manifold flow, the first known application of CFD to rocket propulsion systems, which led to the scrapping of the engine's 3-duct design for a better performing 2-duct design. In 1984, the first computer was installed at the Central Computing Facility at Ames for the NAS project, and of course the computer was a Cray. In this case, it was the Cray XMP, a follow-up to the Cray 1, developed by teams at Cray Research. Released in 1982, the computer was described as a cleaned-up successor to the Cray 1 and was the world's fastest computer from 1983 to 1985. Though the XMP had quad-processor versions, the computer installed at Ames was a single-processor version, capable of 210 megaflops in peak performance. Though that seemed very impressive in its time, those are actually speeds that were 100 times slower than a modern smartphone. Ames expanded the project beginning in 1985, when construction began on a new facility that could house computational fluid dynamics experts with computer scientists and other experts in a collaborative environment. In 1986, NAS became an Ames division, and in 1987 moved into the new 90,000 square foot building, along with a new Cray 2 computer named Navier, after Claude Louis Navier, one of the developers of the Navier-Stokes fluid dynamics equations. The original NAS facility was meant to provide NASA and other researchers leading-edge computational capabilities based on an innovative and network-centric environment. A second Cray 2 arrived in 1988. Researchers there would pioneer many important innovations. It was at the NAS division that the Unix operating system was first used on supercomputers. During the 1990s, nearly all supercomputers used Unix, although today all supercomputers run on the Unix-like Linux operating system. The NAS division was responsible for linking supercomputers and workstations together to distribute computation, and were the first to use TCP to connect remote users to supercomputing resources with the creation of NASNet in 1985. These early supercomputers allowed incredibly advanced work to be done via computing, such as studying pressure distributions in space shuttles' engines and vortex flows over the wing surfaces of the F-16. NASA researchers used NAS supercomputer resources to study the failure of the O-ring in the Challenger disaster, which resulted in the largest 3D structural simulation in the world at the time. Thanks specifically to the power of supercomputers and advancements in computational fluid dynamic equations and visualization software. Visualization of the data resulting from the computer's calculations is a significant part of CFD analysis. It has been significantly improved thanks to work at Ames. In 1984, the NAS division purchased a number of graphics terminals from a new company called Silicon Graphics to improve data visualizations. NAS continued to work with Silicon Graphics for many years, co-developing numerous computer advancements. The initial Cray computers had a unique appearance, with large towers arranged in a C-shape with a surrounding shelf that contained some parts of the computer and could be used as a bench. In the film Sneakers, two characters have a discussion while sitting on a Cray YMP. The Cray 2 lacked the bench, but maintained the C-shape. NAS continued to upgrade with new computers, such as the 16,000 CPU Massively Parallel Connection Machine 2 in 1987, along with numerous other machines. NAS, in partnership with DARPA and the University of California at Berkeley, also developed the Redundant Array of Inexpensive Disks program, known as RAID, which led directly to today's distributed data storage technology. The work done at NAS, today the NASA Advanced Supercomputing Division, in computational fluid dynamics and more, has been instrumental in better understanding complex calculations and physical interactions, such as work on understanding vertical and short takeoff and landing flows. The NAS Parallel Benchmarks, released in 1991, was used to evaluate the performance of supercomputers in CFD applications. By 1988, the 8-processor Cray YMP met NAS's goal of sustained gigaflop performance for CFD applications. In 1990, NAS developed the Virtual Wind Tunnel, using virtual reality to create a highly interactive visualization tool to study fluid dynamics. CFD has allowed early testing to reduce or avoid the need for expensive wind tunnel tests and has been used repeatedly in the development of aircraft like the FA-18 and the design work on the never-finished X-30 aerospace plane. Currently, CFD is being extensively used to support development of both the X-59 Quiet Supersonic and the X-57 Electric Concept aircraft. NAS supercomputers, currently there are 4, Pleiades, Endeavour, Electra, and Aiken, have also helped in other modeling efforts, such as cloud simulations on Earth and other planets, climate and ocean circulation simulations, and the development of the DeBakey Ventricular Assist device, used to help patients in heart failure stay alive while waiting for transplants. Other developments help researchers study the potential of carbon nanotubes and analyze materials at the atomic level. The NASA Advanced Supercomputing Division continues to be a center for supercomputer work, both in the development of more powerful supercomputers, such as Aiken, which is NASA's most advanced supercomputer to date and is housed in the Supercomputing Modular Facility at Ames, and is a resource for an incredible amount of research, pushing boundaries in aerospace, climatology, and countless other fields. Faster and more powerful supercomputers continue to be developed, and today supercomputer performance is measured in petaflops, which is a quadrillion floating point operations per second, or even exaflops, a quintillion flops. The NASA Advanced Supercomputing Division has facilitated and participated in world-changing research, both in practical application and in our understanding of the universe, and will most certainly continue to play a large role in the technologies and advancements of the future. I hope you enjoyed this episode of The History Guy. Check out our community on thehistoryguideguild.locals.com, our webpage at thehistoryguide.com, and our merchandise at teespring.com, or book a special message from The History Guy on Cameo. And if you'd like more episodes of Forgotten History, all you have to do is subscribe.